Hello, welcome to CSC 7013, Advanced Mathematics for Computer Scientists. I'm your instructor, Dr. Z Zhang. As you know, the previous video lectures were given by Dr. Chen, but I decided to cover this last video lecture myself. Today, we're starting a new chapter, a new topic, graph theory. Let's dive in. Graph theory studies the connectivity of different elements represented as dots called vertices, which are connected by edges. And it deals with many interesting problems related to graph connectivity, such as finding the shortest path, which determines the quickest way to travel from one point to another point. And another important application is minimum spanning tree, which is useful in optimizing network connections, minimum spanning tree. Graph theory also addresses many other problems like traveling salesman problems or coloring problems, Eulerian Hamiltonian paths that visit all the sites in a network. In this module, since it is time limited, we will introduce graph theory by studying shortest paths and the minimum spanning tree. Our learning objectives for this module are an introduction to graph theory, Dijkstra's algorithm for solving shortest path problem, and Kruskal's algorithm for finding the minimum spanning tree. What is a graph? Graphs are data structures used to represent connections between pair of elements. Okay, usually the elements, also called nodes, also represent with a circle. Okay, nodes represented with a circle, like this. And I also note this is a node. And or you can call it vertices, vertex. Okay, and then the connections are represented by the edge. Okay, and if you apply to the network, you can call it a link. So, okay, the graphs are directly applicable for many real-world scenarios. For example, we could use graph to model transportation network where nodes would represent facilities that send or receive products. So these are the storage places or front premises and send products, or the data network, or these are maybe the routers and so on. So this is a graph, nodes and edges. One of the simplest scenarios where you might use a graph is to model the roads and destinations. In a graph like this, the nodes represent different houses, different destinations, and visiting points, while the edges represent streets, roads, connecting them. With a graph like this, you can analyze the best way to travel from one point to another point. Now we come to the mathematical definition of a graph. It's simple. Okay, a graph, as we talk about, is like a set of nodes. With a set of nodes, we divide it by, or vertices. So vertices, and so we call it, and a set of link or edges connecting them. That's a set. Okay, the number of nodes may or may not have to be the same as the number of links. You can have more links, different kind of link between the lines, and so on. So it's denoted like this. So where V means the set of the vertices or nodes, and E is the set of the edges. A graph can be also there are two types. The link can be directed or undirected. So undirected using the example of the roads, it's like a two-way street. So the undirected is denoted by a straight line. A directed, kind of like a one-way street. You can only go from one. A direct link like this, kind of like a one-way. So like this. So directed or undirected. So that's easy. That's a notation of a graph. So now, a graph is an ordered pair of two sets, a set of nodes and a set of links or edges. In addition to these basic components, the graph can have an additional feature where each link is assigned a weight. And this weight could represent the length of the road or the cost of communication or some other measurable quantities. For example, and this edge, its weight is 9, and this weight 8, and this link from 1 to 2 is 6, and so on. Here is a weighted and directed graph. You see, each of the link has a weight representing its cost, or if it's a road, it's how long the distance is. If the communication link is what's the cost of the communication. And in addition to that, it's a directed graph, and each link will have directions. In other words, this may be one way, going communication this way, but not that way. And this one goes from 0 to 2 only, but not 2 to 8. That's equivalent to an infinite cost. The first problem we are going to explore in graph theory is the shortest path problem. Okay, say you have a graph representing the destination in a traffic system, and if you say you want to get from A to B, so that's the C, that's the D, and which way is shortest path? If let's say each road will have different weight, so say 2, 3, and 1, and 1.5. Okay, you want the total cost be the lowest. You're adding up all the links along the way. So apparently there are two routes too. One is from here, A to C and to B. Another one is A to D and to B. Which one do you think is shortest? Adding the weight. Obviously it is the lower path, is from here, because the total distance is 2.5 and above is 5. So in this simple one is kind of hard to find out, but kind of easy to spot. You don't really need the calculation. But if you have a very sophisticated graph, you want to find out all connected, very complex connections, and this problem is not that straightforward. It's not intuitive. That's what this Dijkstra program is for. For example, from here, A to B, and what is shortest path if you have all this link, and the answer is not that obvious. So that's what this Dijkstra algorithm is for. Okay, and this algorithm is used in many applications, including the GPS device, to locate the shortest path between current location and the destination. And this algorithm was created by and published by Dutch computer scientist Dr. Edgar W. Dijkstra. Alright, so the basics of Dijkstra's algorithm for finding the shortest distance from a source node for all graph. which means all the Dijkstra's algorithm starts with the source node, and it starts with the source, calculates the shortest path from its node to all other nodes in a graph. The algorithm maintains a tentative short path distance, right, as tentative shortest path, and then update. Okay, it starts from the source and then find the shortest path to all. Okay, from the source to all. And once the node's shortest path is finalized, it was the visit. The important is the visit. I will talk about that in an example next. Visit. And then the algorithm proceeds by selecting unvisited. You only visit one node once. It's just a visit and visit and visit and visit. Once it's all visited and the whole thing is done, you only visit a node once with smallest tentative distance and repeating the process until all nodes has been visited. At the end of the algorithm, the shortest path from the source code, source nodes, to all is found out. So, and then that's forming a shortest path tree. All the nodes could be connected. Okay, that's shortest path, and it's a tree, all with the source at the root, and all the shortest path through its leaves, if you will. Now, let's go over the pseudocode for Dijkstra's algorithm. You can go over this one by one as yourself and just invent your own graph. Now, I'm using this one. Okay, so I have this graph shown on the right, and then first step, set all the distance to infinity. So I will use green, so that infinity, and this first one is 0. So let me go 0. So now to start, okay, and select unvisited nodes. So whenever I visit a node, I will circle it green. All right, so select the unvisited nodes with smallest tentative distance. Well, that obviously is 0. So I will select this one. All right, so then mark it as a current node, as visited. So number 0 is being visited. What I do when I visit, and then I update these neighboring nodes. All right, I update nodes by adding the link to the current weight and update. But when I update, I will see if they already have the shortest distance. If the new distance is less than their already assigned distance, I will update. Otherwise, I will let it stay as it is. But in the first step, obviously, I update. So this one's already infinity. So from here, 0 plus 1, and then to the first node, and then obviously it's 1. So it's updated. So it's 1. So 0 plus 4, and that's 4. Updated. No longer it's infinity. And 0 plus 10, it's 10, because 10 is less than infinity, so it's 10. So now what do you do? And then new distance, and then select. Okay, now next one, and go back. Okay, select the unvisited nodes with smallest tentative distance. So for the next visit. So I will here, and which one is the smallest? This one is 1, that one is 4, that one is 10, so therefore I will select this one to visit. All right, so when you visit, okay, let's see, 3 steps. Visit, update, and then choose next visit. Once again, 3 steps. Visit, update the neighbors if you can, and then select the next visit. So now I selected next visit. Now I have only one neighbor. Okay, or let's make it interesting. If you have one line here with, say, a weight 1. Okay, so then, so this neighbor update is 4, and this is 2, so they will be updated to 2. Okay, so that will be updated 2 because that's less one too. So now update this one 4 and 1 and 2, and this will be updated to 2. So then, okay, so now it's done. So once again, I will choose ones with the unvisited, with the smallest one. Then I will visit this one. So that's 2. That's okay. That's 3. Okay, so I will visit this one. So that's 3. But then I visited this one, but then there's no neighbor. This is already visited, so I will stop there. And next I will visit this one. So next I will visit this one, and so this is number 4. So that's 3. So there's only one neighbor. So update. So I will be 3 plus 3, that's 5. Okay, it's 5. So then there's no other choice but to visit this one because unvisited. You have only visit unvisited. And then this one, so plus this 5 plus 3. 3 is 8 is less than that. This is 8. Okay, and then what to do? Only thing next visit is visit this one. Okay, visit this one, and then you will have update. So this one is 8 plus 1. Okay, so this will be 9. 9 is less than 10, therefore 9. So then, which one to visit? Last one to visit is this. But when you visit, update, and then choose to next it. So I visit number 3, update. There is no need to update because if you that's 0, there's no need to update. And select. Well, there's no way to select. Everything is visited, so done. So from here, you can see the shortest path tree. Now, let me draw the shortest path tree. Let me changing the color. Okay, I just use this one. So from 0. Okay, and then you go from 1. Okay, and then 1. So this one is 2. So you go 2, now go to 4, so that you will have 1, 1, you have a 2. So that since that link is 1, and then you go to 4, and then that part is easy, go to 5, and then 6. Okay, that part is interesting. So even though if you, to begin with, you go to 3, but then you finally figure out that's the shortest path, and then you actually go to 3. So let me put down the okay, the actual shortest path. This is 0, so that is 1, and that will be 2, that will be, so that is, okay, that is 1, 3, 5, okay, and 8, that will be 9. That's shortest path. This is a shortest path tree. Shortest path tree looks like this. But then notice the shortest path tree is not necessarily match with this visiting sequence. A common mistake is that you think the shortest path tree is a sequence. No, for example, this case, I go here, here, and visit number 3, and then finally I figure out the actual shortest path for 3 is going all around here to 3. But if you just follow the algorithm, it will figure out. So now, and also the visiting sequence, sometimes that also form a tree. The visiting sequence, when a sequence, the node gets visited, so it's
Not necessarily, most of the time it's 0. So we visited 0 first, we visited 1, it's a sequence, and we visited 2, and then we jump back to 4, and then we go to 5, and then it's 6, and then finally 3. Not. Okay, your update doesn't mean visit. So the idea here is you look through this, simply step. Let me make it simple. Okay, and visit. Okay, update. And then choose next visit. And then continue. When all visited, done. So it's like one way. Visit, update 1, 2, 3. Choose, and then next visit. So of course, you go follow this algorithm, you will see this way. And no matter how complicated it is, you can always find the shortest path. Okay, there's a proof why this way works, but then we'll go over slightly, but you can just amuse yourself by creating a graph, see if you can find the shortest path. Okay, this is an informal explanation of why Dijkstra's algorithm work for finding the shortest path. Okay, it's based on the philosophy that it works on the basis that any subpath of the shortest path between the original vertex and the destination is also the shortest path. So what does that mean? So for example, we find the shortest path from A to B is this. Okay, and then anything in between, so from C to D is also the shortest path. Okay, and that is also the D, C to E is also the shortest path. Why? Because we always remember what we do. We update the neighbors. We choose the neighboring shortest distance to visit. So we then update whenever the distance is shorter, and we update it. And therefore, we guarantee that this shortest path, the subpath, is also the shortest path between the subnodes. And also it works for the directed or undirected nodes. You can make the same argument. However, one stipulation or one exception using the algorithm is that the graph needs to be non-negative weights. Okay, the weight has to be either 0 or positive on every edge. This is because during that process, if the weights of the edge have been negative, you keep on adding. If you're going a circle, it gets lower and lower and lower. So this algorithm will become an infinite cycle. You get lower. But whenever it is positive, you always find the minimum because you keep on adding the distance, you find the minimum path. If the distance is negative, you go a circle, you get a lower, 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 and then of course that defeats the original purpose. We're trying to find the shortest path. Well, practice make it perfect. Here's another example. Let's go through the algorithm. Remember, visit and update and choose and then visit and cycles until all the nodes are visited. Now let me using this one because I already did, but I just go over. You can use this my notation. So obviously I visited 0. So the weight I was do 0 from 0. Okay, and then update. So then number 4. We note update doesn't mean visit. So I will have 4. The distance is 4 through 1. And update nodes 2. I will have 9 through 1. So which means distance 9 go through 1. So now I'm going to choose. What do you do? Choose the lowest tentative distance to visit. Now, visit number 3. Once again, visit number 3. So now update. So then from here, I have 8, and then that 9, compare 8 and 9, so 8 wings because it's smaller, so therefore 8, distance 8 through 3, so distance 8 through 3, update it. And also I update this one, number 5, so that's 4 plus 13, 17 through 3. Okay, update it. Now choose. Okay, which one? Choose 8 and 17. Obviously, 8 is the choice, so I visit number 2. Okay, that's the third visit. Now, what visit? I will update. Okay, and that will be 20, number 4 over 2. And then over here, 8 plus a 5, it's 11 over 2. So compared to 17 over 3, so that's wings. So they're updated to this. This one is updated to 17. So it's through 2, so which means the path goes through there. So then choose. Okay, I'm here. Choose that one is 20, and this one is 11. Obviously, 11 wings over. I will visit number 5. Visit, then update. Update over here, neighbor. So 11 plus 3, I get 15. So between 15 and 20. So for number 4, I update to 15 through 5. And then still update here. So 11 plus 15, I get 26 through 5, tentatively. So 26. Now choose which one to visit. That one is 26 and that one is 15. Obviously 15 is the choice. So visit number 4. Then once I visit and then update, okay, there's only one thing to update is the number 15 plus 2. I get 17 through 4. Okay, so 17 and 26 for number 6. So 17 wings, therefore updated to 17. So now which one to visit? Okay, last to visit is this, number 6. So all visited. So from here, you can look at one, this is done. All visited, it is done. So you can draw the shortest path tree. Yes, 0 through 1 using this data. You can, the final data, you can draw the shortest path tree. 8 go through it, and then, so shortest path tree is not the visiting path. Remember, the visiting path or visiting sequence is this, follow the purple one. All right, so this is second example for a directed graph. Okay, you can draw, for base this, you can draw the visiting tree. And now next example, I will use in detail using a table, okay, like we do in the textbook, but exactly the same idea. All right, so this is the second example. For exactly the same graph, I am using this table to illustrate the algorithm, so that for those of you who are text learner would like to read, and I just go over the same graph once. I will represent the data in this table. Node 1, 2, 3, the distance, I updated 0 to source code from 1, and then except this one is 0. Visited, this is a Boolean. If visited, I will put a 1. If it's non-visited, I will put 0. Predecessors, where does it go from? For example, from here to here, the predecessor from 2, predecessor will be 1, and so on. Predecessor, and so when the table is full, then the job is done. Each time I only visit one node. Okay, so start. Initially, the distance from the source is set to infinity, and the distance from node to itself is to 0. Predecessor, so all nodes, yes, not yet determined. The process is determining all the distances, all the predecessors, and then we're done. And all the Boolean variables visited are initially set to 0. And now, so remember, visit, and then update, and then choose. So each of this page, I will have these 3 tasks. Very simple task, but repeating. So each page is 1 step. So now determine, so visit to start, and already updated, and choose node 1 to visit. Remember, number 1. Okay, we are visiting number 1. Node number 1, so see this red is a highlight, which means visited 1. During this visit, I will update. What update? Here and here. So from 2, 9, 4. Predecessors 1, 1, which means 1, 2, and 3 from 1. So this is predecessor determined. And then what? Choose next. So choose next and unvisited, and that obviously is node 3. Why? Because that is updated when node 3 has 4 and that 2 has 9. So this is chosen, so that's 4. So 3, so that is choosing number 3. So remember, next to visit is 3. Now we are visiting node 3. So node 3 is this. Okay, and from node 3, update. Number 2, you get 8. Number 5, you get 17. Predecessors, both number 3. That's done. Updating. Now choose between 8 and 17. Which one is smaller? Obviously 2. So 2 is chosen. So visit number 2. Remember, we're going to visit number 2 in next page. So number 2 is being visited. So number 2 is here. So update neighbors. So they have 2 neighbors. 4, you get 20. 5, you get 13. So 8 plus this, you get 13. Both predecessor from 2. That's update is the red is red. So visiting node 2, you do these updates. 2 and 13, 2 and 13. And then visited. 2 is visited, marked 1. That's visiting with marked 1. So the red is what's done, this step. Okay, it's new. And then choose. Okay, we are visiting 2, between 13 and 20. 13 wins over, and so we choose number 5 to visit. So number 5. Now let's visit node number 5. Well, you probably get bored by now, but actually once saying that, once you get bored, you actually learn. Well, that's a joke. With number 5, so this is what you update from number 5 up to number 4. So you have this, you have 16. All right, so from here plus 3, 13 plus this is 6 plus 3 is 16. And those 13 plus 5, 25, 15, you get 28. So then the updates to both from 5, from here, this, and this. And then which one is visited? Number 5 is visited. So all these are red, color coded. So now you choose next to visit. Once choose an unvisited that has the smallest distance to the source in this node, it is node 4. So between this and that is 2016. So therefore, 16 is chosen. So you go here. Now, once you go here, and then next page. All right, we're about done. Next, we choose next node number 4 to visit. Okay, we choose number 4 to visit. Number 4 to visit, and visit mark number 4 visited. There's only one to update, so number 6. So from 4, which has 16 plus 2, you get 16 plus 2, you get 18. So that's 18, and through number 4. And then what's to do next? There's choosing next to visit. So choose an unvisited node that has the smallest distance to the source. In this case, node number 6. There's only one choice. So only one choice, so no number 6 chosen, so we choose number 6. Okay, the last node to visit is number 6. So number 6, well, we choose to visit. Once again, 3 steps: visit, update, and choose next visit. When you update, you follow this idea. If the new distance is less than existing distance, update. Otherwise, leave it alone. Okay, and also you choose the next to update, and then you will find unvisited, important, and smallest distance. And in this case, you visit number 6, and the distance is 4, from 4, and there's no more. So visited, the last step. So visit nodes and no more. Send you and no more, and then all done. So you're done. So then this table is same as what I draw sketch. In the first example, I just use my hand draw, upload on the graph, kind of messy, but it's contain exactly the same information. You can use this to draw the visiting path and the shortest path tree. Okay, now we find the table. I contain all the information of the shortest path, all the neighbors of node 6 marked visited, and we have the final result, a shortest path from node 1 to each node of the graph. We can clearly see from the diagram that the shortest path from node 1 to 6 is this. So how do you do that? You trace back 6 and the predecessor 4, and you go actually backwards. And then 4, you go to 4, and predecessor 5, and then 6 is 5, and then 5, you predecessor 2, and then you go 2, and then 2, you go to 3, and 3 go to 1. So that's, but you go to backwards in this way. And this is another way to do this. In fact, once you have to solve the whole graph for every node altogether, even if you just want to know from 1 to 6, but in fact the process visit all the nodes. In fact, as a result, all the shortest path from the source to any nodes is being found out. So in this case, the shortest path is from 1, 3, 2, 5, 4, 6. So that is shortest path, and with the distance 18. So it's going this way. This, and this. Not this, because that's a long, costly route. Interestingly, the process of finding the shortest path to all nodes, okay, and you find one, you find all nodes. Additionally, shortest path can be viewed as a structure known as shortest path tree. I'm sure you know the tree structure, which easily constructed using the predecessor information from the table obtained. You can easily construct a tree by drawing this, but in this, for example, that was interesting. Well, not so interesting, but it just, this time it has only one branch. Oh, not even a branch, but just all connected. And some other graph may actually form a tree structure, have a branch to all directions. And then algorithm can also be viewed as a series of a visit or visiting sequence. Important thing to point out is the sequence of visit, where is also known as search path. Okay, the search path, however, is not to be confused with the shortest path. But while they may be overlap, unfortunately, in this case, they are the same. So this is a sequence of the search path, and this is a sequence of the shortest path tree. They are, in this particular case, they are the same, but only in this case. As you see in the example, there are two different concepts. The search path is the sequence in time, the visit, because you have to choose the smallest path and unvisited that uniquely define which one to visit. All right, so small list unvisited, and then you just, that's the search path. Okay, and the shortest path you can construct from this. Let's see an example of the another example, just to show that the search path and the shortest path tree are actually different idea. Now, let's use one more example to see the difference between the shortest path tree and the search path or visit sequence. So let's carry out this algorithm again. So first, of course, we have set the distance to be infinity except 0. We get 1. So first of all, choose one that has the smallest distance and to visit. So we visit this one, obviously, and then visit, update. So what do we update? So that one is infinity and 1, so this update to 1. And then this one is infinity and update to 4. And that's infinity and 12 to update to 12. So now we update it, 3, and then choose the smallest to visit next. Obviously, that's the first one, so that's the one visit. Now, once visit, the task to complete for visiting is updates. So they have 2 neighbors, from 1 plus 2, okay, and I get 3, so 4 and 3, so then 4 change it to 3 through 1, right, because that's 4 changes to 3. So then update this, infinity change it to 4. So change it to 4. So 4, infinity change to 4, 4 through 1. So now update it. One is 3, another one is 4, and choose the smallest to visit and visit this. Remember, so this one is first this, and then, so the visit sequence, I will do this. Visit sequence is 0 and 1 and then 2, right, 2, but then there's nothing to update because all surrounding are already visited, so the visit, and then choose next smallest distance to visit, and obviously next one is unvisited, and that's the 4, so the 4 to visit, so the visit 4, okay, and then visit 4, the task to update, so the 4 plus 2, you get 6 through 4, right, so that's 6 through 4, and then update it, and then there's only 1, so obviously you have only one choice because there's smallest unvisited. Okay, there's all these are visited, the rest are infinity, so you go choose this to visit. All right, so then visit and then update. So update this one, so 6, then we'll get 9. All right, so it's 6 plus 9 through 5. So that's, this one is a 9. So then where to visit? And next one is 9 because I'm visited there. The rest you only visit once. So it's this one. And you only visit once. Next choice is 6. So you visit 6, then update. Visit 6, then you update this one, and then 9 plus 1, you get 10 through 6. So between 10 and 12. So I choose this, so that's 1. So update to 10. So then visit, and then nothing to do. Of course, last one visit is this. So let's see, we update 4, this visited 5, visited 6, and then visited 3. Okay, so that's search path. All right, so, but then the smallest path. shortest path is something different. So then shortest path, you have to look at the predecessor. Of course, from 0 and to 1 is the shortest path. Okay, and the 2 is obviously go through, okay, 2, you actually goes through 1. So that's going, the 2 actually goes through here. And then 4. And then 5, 6, 3. So the shortest path, so this is shortest path tree. It's a tree, it has a branch over here. So the visited search path is this, is a sequence. So that's when I draw the green circles. This, that's the sequence. So search path tree, but then the tree is this, from this, so from 0 to, for example, you want to visit 2, you go through 1, not directly go to 2, because you directly go to 2, you get a 4. But this one, now, if we label the distance, and so that one is 1, from 2, you get 3, from 4, you get to 4, and then 5, you get 6, and 6, you have 9, 3, 3, you get 10, not 12. So that's shortest path tree, and that's search path. So that's different, and could be quite different for complicated So we actually have 4 examples. Hopefully you master the shortest path search, the Dijkstra's algorithm. You can amuse yourself by creating your own diagram or graph and work it out, and you practice, make it perfect, as we say. All right, hope you enjoyed it.